All right, we're in section 4.2 and we're talking about Rolle's theorem and the mean value theorem. In the last video, I had gone over Rolle's theorem, and so I'm just going to quick recap that. Rolle's theorem said let f be a continuous function on a closed interval ab, differentiable on the open interval ab, and f of a equaling f of b. If these three conditions are satisfied, then there exists a number c in the open interval ab so that f prime of c equals 0. Rolle's theorem will give you a guarantee that you have a local max or a local min between A and B, all right, if these three conditions are satisfied. Rolle's theorem can also be helpful in solving equations. Okay, we looked at an example here. This was the last thing that we did in the previous video. And that's where we had left off. Okay, so let's take a look at the mean value theorem. Rolle's theorem is actually a special case of the mean value theorem. I'm going to let the letters MVT mean mean value theorem, okay, if I have to refer to that. And I will refer to this for something else later down the road, okay. Let's let f be a continuous function on a closed interval ab and differentiable on the open interval ab. If you have these two conditions, then there exists a number c in the open interval ab so that f prime of c is equal to f of b minus f of a over b minus a. All right, now here's a picture of what's going on. So I have two numbers, a and b. Okay, and here's f of a and here's f of b. Now, I'm going to go ahead and draw a line between those 2 points. F of b minus f of a is the difference in the y values for these 2 points. B minus a is the difference in the x values for these 2 points. Or this is just the slope of the line passing through these 2 points. F prime of c is also slope of a tangent line. So the mean values theorem says that if you have these two conditions satisfied, you've got a continuous function on a closed interval and it's also differentiable on the open interval, then somewhere between these two numbers, a and b, there's going to be another number, c, such that when you come up to the curve and draw a tangent line, the slope of this tangent line is going to be the same slope as the line passing through these 2 points, a f of a and b f of b. Okay? Now, Rolle's theorem is a special case of the mean value theorem. Since Rolle's theorem has 3 conditions, the mean value theorem has 2 conditions. Okay, the third condition for Rolle's theorem is that f of a and f of b are the same number. Well, if f of a and f of b are the same number, f prime of c is 0, right? Well, that's the conclusion of Rolle's theorem. Okay, and if f of a and f of b are the same number, then these 2 points would be at exactly the same height. And so if I draw a line passing through those 2 points, it would be a horizontal line. Well, somewhere between a and b, there's going to be another spot where you come up to the curve and draw a tangent line that would also be a horizontal line. So Rolle's theorem is, again, just a special version of the mean value theorem. The mean value theorem is the kind of the more general form now, saying that the slope doesn't have to be 0, but there's somewhere between a and b, there's going to be another number that would produce a tangent line with a slope that is the same as this line passing through these 2 points, a f of a and b f of b. All right, let's take a look at a proof of this. So the line that is joining a f of a and b f of b is represented by the equation using point slope form. Y minus y1 would be f of a equals the slope. Okay, the slope of this line would be f of b minus f of a over b minus a times x minus x1 would be a. I'm going to let the function g of x be equal to f of x minus y. Y is right here. Okay, so if I add f of a to both sides, and now I'm subtracting y, right? So I'd want that minus to come into that term at the end there. Then g of a and g of b would be the same. Let me verify that. Okay, so here's g of x. G of a would be f of a minus f of a, that's 0. And then here's a minus a, that's 0. 0 times anything is 0. Okay, so g of a would be 0. How about g of b? Well, if I plug b into g, I would have, here's b minus a, which you can cancel with b minus a here. And then f of b minus f of b, that's 0. And then f of a minus f of a, that would be 0. So I end up getting 0. G of a and g of b are the same because you get 0. Now g is differentiable. How do I know that? G is just this function that I came up with, you know, to have this work out here. But how do I know g is differentiable? Well, f is differentiable, and y is a line. A line is differentiable anywhere. So you've got a differentiable function minus a differentiable function that will produce a differentiable function. So g is differentiable. So by Rolle's theorem, and by the way, g being differentiable also means that g is continuous. We saw a theorem at the end of section 2.8 that said that if you have a differentiable function, it will always be continuous. Now, I also mentioned that when we had talked about that, you got to be careful about how you read that, because some students want to flip that and say if you have a continuous function, it's differentiable. That's not true. Okay, if you have like a V-shaped graph, yeah, you're continuous, but you're not differentiable at the sharp turn. Okay. So g is differentiable and therefore continuous. So by Rolle's theorem, and I've satisfied the two conditions, right? G is differentiable and continuous. So by Rolle's theorem, and g of a and g of b are the same, right? That's the three conditions on Rolle's theorem. Continuous, differentiable, g of a equal g of b. I verified that. So by Rolle's theorem, there exists a number c in the open interval ab such that g prime of c is equal to 0. Okay, well, if g prime of c is equal to 0, and here's g of x, then g prime of c would be f prime of c minus y prime. Okay, so I've got f prime of c minus y prime. Well, y is a line, right? So y prime would be just the slope of that line. F of b minus f of a over b minus a. And if you add that number, f of b minus f of a over b minus a, to the other side here, then f prime of c is f of b minus f of a over b minus a, and that's where I had to get to. That's what I had to show. Okay. Let's take a look at an example of using the mean value theorem. If f of x is equal to 5 minus 4 over x, find all the values of c in the open interval 1, 4, so that f prime of c is equal to f of 4 minus f of 1 over 4 minus 1. Okay, well, f prime of c is equal to f of 4 minus f of 1 over 4 minus 1. Here's f of x. So f of 4 would be 5 minus 4 over 4 is 1. 5 minus 1 is 4. F of 1, 5 minus 4 is 1, divided by 4 minus 1. Okay, 3 over 3 is 1. F prime of c, well, here's f of x. So f prime of c, I can differentiate, directly. Derivative of a constant is 0, and then minus the derivative of 4 over c. Well, that would be a quotient rule, right? I could take the bottom times the derivative of the top, that'd be 0, minus a negative means I'm adding. The top times the derivative of the bottom is 1, all over the denominator squared. So I'd be dividing by c squared. Okay, here's f prime of c is 1. Here's f prime of c is 4 over c squared. So I'd set those two equal to each other, and I can solve this equation then for c. c is equal to plus or minus 2. Now, negative 2 is not on this interval here. Okay, pay attention to the interval that is given. And C is 2, and that'd be my answer. Okay, now here's a picture of what we're doing. I've got this curve f of x, or part of the curve drawn, okay, and 1, 1 is on the graph, 4, 4 is also on the graph. C is 2. So if I plug 2 into the function, 5 minus 2 is 3. Okay, here's 2, 3 on the graph. Now, if I draw a line between the points 1, 1 and 4, 1, the slope of that line is 1. Well, at this spot here when C is 2, and I come up to this point, the slope of the tangent line would be the same. It's going to be 1. Okay, so that's all we're showing here. All right, somewhere between 1 and 4, you're going to have another tangent line producing a slope of 1. The main significance of the mean value theorem is that it allows us to obtain information about a function from information about its derivative. Let's take a look at an example showing what I mean by this here. Okay, suppose that f of 0 is negative 5 and f prime of x is less than or equal to 7 for all values of x. How large can f of 3 be? Well, I have no idea what this function is. Like, I don't have a formula or anything like that for f of x, right? All I know is one point on the graph, and I know that f prime of x is less than or equal to 7 for all values of x. How large can f of 3 possibly be? Well, I can be able to figure that out by using the mean value theorem. F is differentiable because f prime of x exists for all values of x. F prime of x is less than or equal to 7, they told me, right? So f prime of x exists for all values of x. And if you have a differentiable function, it will be continuous. Again, that was the last theorem that we looked at in section 2.8. Now that's the two conditions that I need to be able to use the mean value theorem, right? I need a differentiable function, and it's got to be continuous. Okay, so then there exists a number c in the open interval ab, so that f prime of c is equal to f of b minus f of a over b minus a. Well, let's apply that here. Okay, so there exists a number c in the open interval 0 to 3. Okay, that's what I care about here. We can apply the mean value theorem on the interval 0 to 3. We can apply it anywhere that we want, but using the information that is given here, when we're going 0 to 3, then there exists a number, c, between those other two, so that f prime of c is equal to f of 3 minus f of 0 over 3 minus 0. Okay, well, let me multiply both sides of this equation by 3. And let's also add f of 0. Okay, so then f of 3 would be all alone there on the one side. F of 3 would be f of 0 plus 3 times f prime of c. Now I want to know how large f of 3 can possibly be here. F of 0 is negative 5. So I got negative 5 plus 3 times f prime of c. Well, f prime of x is less than or equal to 7 for all x. So f prime of c is going to be less than or equal to 7, no matter what number this is. Negative 5 plus 3 times f prime of c is going to be less than or equal to negative 5 plus 3 times 7, since 3 is the biggest possible value that you can have for the derivative. Negative 5 plus 21 is 16. So the largest possible value that f of 3 can be is 16. Now that's pretty neat, because again, I have no idea what f of x is. They're not giving me a formula for f of x. I have no idea what the graph looks like or anything like that. Like I said, all I know is that I've got 1 point on this curve, and f prime of x is less than or equal to 7 for all values of x. Well, that allows me to get some information about a function from information about its derivative. Okay, which is kind of neat. And so that's one useful thing about the mean value theorem. Okay. All right. So of course, like anything else that we are doing here, when they ask you to use Rolle's theorem or the mean value theorem, make sure that you're clear in the wording. Okay, they will have you prove some things in this section using the mean value theorem or Rolle's theorem. Okay, make sure that you're clear. Make sure that the notation looks good. As we've been doing. So here's the homework on page 291. Be sure to look at the odd numbered problems listed.